So we're talking about RSA. And RSA is a public key encryption method, which simply means that the key doesn't have to be secret. Normally when you make a code, you want the sender and the receiver to be the only ones knowing the key to crack the code. With RSA, we use a public key, which anybody can have the key. But unless you have the information as to how the key was built, knowing the key is no benefit to you. It's called RSA after its inventors, Rivest, Shamir, and Adelman. Once these messages have been converted into a numeric form, remember with codes, we turn letters into numbers. I mean, we're looking at a function here to do the coding for us, so we need numerical things to do the calculation on. Can't do the calculation on letters. So we take our message and we turn it into digits. We then encipher the digits using modular exponentiation, in which each digit is raised to the e power, and we do this calculation in Zn. So you remember, we're working with mod n stuff. And when you mod n, what could you get for your answers after doing the arithmetic? No, mod n. We divide out n. What are we left with? Remainders. And the remainders can be what? Up to n minus 1. So 0, 1, 2, through n minus 1. Okay? Plain text digit is going to be symbolized with P sub I, because we don't know how many digits are going to be in this message, so we'll talk about the general one, PI, is ciphered into ciphertext digit CI, where CI is PI to the eth power mod n. So we're going to take the digit P, raise it to some exponent e, which is a fixed number, and then mod n, which is another fixed number that will be determined. Once we do that, we get a new number. That new number is the coded number. Then has to be decoded once received. CI is a number between 0 and n. Remember, they're remainders. They're less than n. 0 and n minus 1, basically. Or 0 through n minus 1. So n must be chosen large enough to cover all the possible plain text digits. If your n is 5 and you have the whole alphabet to encode, you're only going to get 5 different answers when you code the things. Well, that won't work, because if an A and a Q both turn out to be the number 4, when you go to decode it, you have the number 4, and you need to figure out that that was either an A or a Q, but you don't know which one it was. So we have to make sure that the answers after we mod n cover all the symbols that we need coded. And that might mean what? If we're doing the alphabet, we need 26 for if we're not worried about upper lower case. If we're worried about upper lower case, now we have 52, plus we have space, periods, all the special symbols. So you want to make sure n's big enough to cover everything that could possibly happen. All right? The n in RSA is chosen by multiplying two very large prime numbers, somewhere around 200 digits each. So that after multiplying, then you have numbers that are at least how many digits? 400. So you're dealing with a very big N. But multiplying those 200-digit numbers together is a rather easy thing to do, and a computer can do it rather quickly. To decipher the message requires taking that N value, that is the product of two very large prime numbers, and factoring that N into those two very large prime numbers. Factoring a 400-digit number, basically. Not something that you probably want to sit down and do in your lifetime. This is an unrealistic thing for even the fastest computers to do. It would take them many, many more years to figure out what your P and Q, your two primes were. Then you have time to decode it, because by the time it finally would able to break the code, the message is out of date. And by then, who cares if it was intercepted or not? For demonstration purposes, we're not going to use very large prime numbers. We're going to use small prime numbers. 5 and 7. Agreed that both of those are prime? So N is what? 5 times 7, or 35. Not a very large N. Now remember, that N is known. It's a public key. Can you look at that and factor it if you didn't know what was on the screen? If I tell you 35, write it as the product of two primes. Would it take you very long to do that? No. Remember, in real life, we're working with a 400-digit number. Would you be able to do that very easily? No. So understand that this is for purposes of demonstration only. We're working with smaller numbers so we don't get overwhelmed. Okay? But the process is what's important. So this is a very small number, and it's easy to factor, right? So the next step is to compute the magic number B. Now this number B is going to be important in the decoding part, and somewhat important in the coding part, but more important in the decoding part. B is P minus 1 times Q minus 1. So you take your two primes and you reduce them by 1 and multiply that product, those differences together. So, what is P minus 1 times Q minus 1? 4. And you got that by 4 times 6, right? So the exponent that you choose in your RSA encryption or enciphering is a number that has to be relatively prime with 24. B will always be even, because P and Q are large prime numbers, which means they're odd, because there's only one even prime number. What's that? 2. All the other prime numbers can't be even. If they were even, they would be divisible by 2, right? Good. So E has to be an odd integer that is relatively prime with B. Now B's even. That's why E has to be odd, because if E was even, they would have a common factor of 2. Possibly other ones, but they would definitely have a common factor of 2. And for relatively prime, we want what for the only common factor? 1. Good. So we need to choose E and then verify that the GCD of E and B is 1. So not every odd number will work, but a lot of them will work. So finding E is kind of difficult in that you have to pick the right value for E, but there's so many of them that work that that's not like finding a needle in a haystack. You just pick an odd number and try it. If it works, great. If it doesn't, meaning it's not relatively prime with B, then what do? Pick another one. So it could take a little while to get the right E, but it's not that difficult to do. Yeah?
But E itself doesn't have to be prime.
No, E does not have to be prime. Of course, if it was, then that would be relatively prime with B, wouldn't it?
Yeah.
So picking an odd prime, a large odd prime or an odd prime would be a good choice for you, wouldn't it? Recall that B was 24. Put that up there because the previous slide's now no longer in front of me. E is 55. The GCD of E and B will be the GCD of 55 and 24. Now I've color-coded them so that when we work with this, you can see where the numbers are transitioning to. Because you remember when we did this, we started with what? We're going to use Euclid's algorithm. Remember that?
Yeah.
We start with the largest of those two numbers. So we started with 55 and we divided it by 24. And how many times will 24 go into 55? Twice. And 2 times 24 is 48, and that leaves 7 left over. And then when we do the next step, we divide into what? 24. And what is it that we divide into 24?
7.
7. Good. And it goes 3 times, but that's only, and so we have 3 left over. Then we divide 7 by 3, and it goes twice with a remainder of 1. 3 divided by 1 goes 3 with a remainder of, and that's what we're looking for because that tells us we're done with the Euclid's algorithm. What's the GCD then? 1. The last non-zero remainder. So the GCD of 55 and 24 is indeed 1. Now you'll notice I didn't pick a prime. I picked an odd number that wasn't prime. But it is still relatively prime with 24. So E equal 55 would be a valid exponent to use. Now suppose we wanted to decipher the plain text digit 9. So we've taken whatever code it was. It could have been a letter that got changed into a number, the 9th letter in the alphabet maybe, or it could be the number 9. Maybe our code has numbers in it. Right? But you need it to be a numeric code, or a numeric message to start with. And so what we need to do to code it, or to encipher it, is to what? Raise it to the 55th power and mod it by our n, which was 35. And I probably should have reminded you what n was. I didn't put that up there. Apologize for that. So, how are you going to do 9 to the 55th power? Well, that's what your calculator's for, right? Yeah. If you tried 9 to the 55th power on your calculator, you get 3.04 3252722 times 10 to the 52nd power. And we want integers, not scientific notation. So even though that is an integer, it's not proper form for us to work with, right? So, computing it directly on our calculator is not reasonable when we have a large exponent or a large base, but the exponent's what's really driving its size, right? So what could we do? Well, we could do 9 times 9, which gives us what? 81, and then we could mod it by 35. Now, how do we do 81 mod 35? You can do it with repeated subtraction, or you can, remember I showed you that trick, divide
Yeah.
81 by 35, subtract the whole digit, that gives you the decimal part of the number, and then multiply by 35, which will turn it into the remainder. Anyway, it turns out, I think, let's see, 11. And then we could do 11, which is 9 times 9, or 9 squared, times 9 again if we wanted to, get 99, and then mod it, and then keep multiplying by 9. Or we could, since we'd get all the way to 55, we probably don't want to just multiply 9 each time, right? But you could do 11 times 11, which would be 9 squared times 9 squared, which would be what? 9 to the 4th. And so now, you notice we skip 9 cubed that way. So that'll speed it up. Once we have 9 to the 4th, we could then do what? Square it. That will give us 9 to the 8th. So we're getting a lot closer than just multiplying by 9 each time, right? Yeah. So that's a little trick that we're going to utilize. To speed the process up, we're going to use the law of exponents and rewrite the exponent 55 as the sum of smaller exponents, and these exponents that we're going to use are powers of 2.